In this problem, we've measured the osmotic pressure at various concentrations of an enzyme, and we're asked to calculate the molecular weight at 25 degrees C. And the data also shows the ratio of the osmotic pressure to the concentration. And notice that it's not constant. So if we think of osmotic pressure equation, and let's look at it for an ideal solution, where the osmotic pressure equals the molar concentration times the gas constant times absolute temperature, or in terms of mass concentration, CS over the molecular weight times RT. Well, the ratio then of the osmotic pressure to the concentration should be a constant, RT over the molecular weight. But it's not for these data, which means we have a non-ideal solution. And so we could model the non-ideal solution. It's sometimes done in terms of osmotic virial coefficients. And so let's look at the case and what we're going to pick. So I'm writing the equation again, slightly rearranged. And then let's try and fit the data where this is the osmotic virial coefficient. And it's related to the fact there are interactions between these solute molecules. So the S is in the concentration indicating a solute. So to then back out the molecular weight, if we were to plot the osmotic pressure and dividing it by RT, the concentration, then 1 over molecular weight would be the intercept, and then B2 over the molecular weight times the concentration, that would be the slope. So I put these data into a spreadsheet and made a plot. So let's look at that plot and then back out the molecular weight and the virial coefficient. So note, in order to make the plot look easier to read and have the y-axis scale, I've multiplied the y-axis by 10 to the fifth. So I have here the equation for just a trend line fit, and you can see the intercept 3.3734. The intercept then, which is the inverse of molecular weight, so 1 over molecular weight. But remember, I've multiplied by 10 to the fifth to get that number, so it means I have to divide by 10 to the fifth. If I do that, then the molecular weight, I calculate 29,644. Of course, not accurate to that many significant figures. So likewise, I can use the slope to get the virial coefficient. So B2 over molecular weight is the slope, and minus 0.0573, again times 10 to the minus 5 because of the scale we picked. And so when I substitute in molecular weight, solve for B2, minus 0.0170 liters per gram. So molecular weight of the enzyme and this virial coefficient, because the solution is not ideal, the equation says as we go to lower and lower concentration, we approach the ideal solution. And that's how we're getting the molecular weight.